came down to you.
Maybe wait just like 1 more minute.
Okay. Experience.
Are we good to go?
Yeah,
Good to
go.
Good afternoon, everyone. Thank you for being at the department seminar. It's my pleasure to introduce Taydra Low. She's a PhD student working with Professor Elizabeth Maroon. She is officially the first member of the Lizard group and also the 11th floor as a grad student. She did her undergrad from Department of Atmospheric and Oceanic Sciences at CU Boulder, and also with a minor in astrophysics. So that's pretty cool. If you don't find her doing Atlantic or North Atlantic climate research in her office, she would be on a walk or a hike with her very cute dog Milo, and also crafting. And recently I learned that she's doing t-shirt designs. So if anyone wants to get their t-shirt design, then she's the person to go to. Also, if anyone has questions on North Atlantic Ocean, she's the person to go to. So with that, take it away.
Thanks, Taydra. Can you guys, oh wait, I'm on you. Can you guys hear me? Good? Sweet. Yes, thanks, Taydra, for the introduction. Today I will be talking to you about new indirect estimates of North Atlantic thermohaline circulation. I would like, obviously, to acknowledge Liz for all of her help, as well as Stephen Yeager at NCAR, and I would like to thank NOAA for funding this project. And also, this is a cool picture that I took when I did field work in the North Atlantic. Don't know where it was. It was a month-long fieldwork trip, so it could be anywhere. So here's a quick outline of my talk. I'll spend a lot of time on the background because I'm giving an ocean talk to, I want to assume, mostly atmosphere people. So I want to make sure that you have a decent enough understanding of what I'll be talking to you about today. So I'll begin by giving a background on thermohaline circulation and AMOC. Then I'll discuss different methods for estimating AMOC, or a different method for estimating AMOC. Then next, I will give you an overview of my science objectives, and then I'll talk about the methods and data I use, and then I will get into my results. So I know some of the atmospheric scientists in this department forget that the ocean exists. So I wanted to remind you that yes, the ocean is in fact real, and ocean circulation, especially North Atlantic circulation, is important for climate. And then earlier this year, Till brought to my attention this study that came out by Renee Van Western. It caused a lot of havoc in the media about potential collapse of AMOC, with headlines like, Atlantic Ocean circulation nearing devastating tipping point, study finds. Critical Atlantic Ocean current system is showing early signs of collapse, prompting warning from scientists. And this other article as well. So these articles demonstrate that North Atlantic circulation is important for climate, and scientists, as well as society, care about its fate. So the reason why we care so much about North Atlantic circulation is because it's a part of the global thermohaline circulation. So thermo meaning temperature, haline meaning salt. This is a buoyancy force circulation, meaning it's dependent on changes in density through changes in ocean temperature and salinity. And most of these changes happen at the surface through heat and freshwater fluxes. And the part that I'm interested in is AMOC, which is this purple box here. And more specifically, the subpolar North Atlantic portion, which is the spread box. And it's because this region is a key global driver of heat, carbon, and freshwater transport, so it has a huge impact on climate. And for funsies, I asked ChatGPT to explain AMOC to a child, not saying that you guys are children, but it compared the ocean to a bowl of soup that's warm on top and cold on the bottom, and AMOC is like a spoon that stirs the soup. So, circulation in the subpolar North Atlantic is made up of a complex system of surface and deep ocean currents, as well as convection zones. Some of these currents you might be familiar with, like the Gulf Stream, the Deep Western Boundary Current. So as water travels poleward, it follows along this Gulf Stream, travels up the North Atlantic Current to the Nordic Seas, where it becomes progressively denser and eventually sinks, or it'll keep traveling around the subpolar gyre and sink in the Erminger or Labrador Sea region. So climate models are important for studying AMOC, but they have long-standing interrelated biases in the North Atlantic. The most noticeable bias is this cold sea surface temperature bias you can see in this red box here. It's also referred to as the blue spot of death, and this bias is shown in both CMIP-5 and CMIP-6 models. The cold bias is also accompanied by a fresh salinity bias, and they originate in the ocean model itself, and that is due to poor representation of the Gulf Stream and the North Atlantic Current. So on the top row, we can see we've got the OMIP-1 and OMIP-2 sea surface temperature cold bias. The only difference between these two models is the forcing that is used to force them. And then on the bottom, you can see you have a fresh salinity bias accompanied with that cold sea surface temperature bias in both OMIP-1 and OMIP-2 models as well. These biases are important because of their potential impact on overturning circulation in the North Atlantic. The sea surface temperature bias can also have consequences for local and downstream climate, which is shown by this study by Keeley et al. 2012, where they took this North Atlantic sea surface temperature bias and used it to force an atmosphere-only model. So on the right side, you can see a difference in mean sea level pressure from the AMIP models or atmosphere-only models forced by the sea surface temperature versus the model forced without it. So you can definitely see that there is impacts on local and downstream climate. So to understand these surface biases in ocean models and how they impact AMOC, we need to have direct observations of AMOC to compare against. And there are a couple of observing arrays that have been deployed, like the Rapid MOCA there, and then the OSNAP array. The Rapid goes from 2004 to present, OSNAP goes from 2014 to 2020, and it's ongoing. These observations are awesome, but they are short and sparse relative to AMOC variability, and so they don't allow for sufficient bias analyses. Therefore, a new method is needed in order to look at how surface processes are related to overturning circulation, and that is water mass transformation. But before I explain what water mass transformation is, I think it's best if I first explain how AMOC is defined so that I can show you how water mass transformation and AMOC are connected. So traditionally, AMOC is defined by the vertically integrated stream function. You can see here in this figure. It's essentially a volume transport. It's represented by sphere drips, which is 10 to the 6 meters cubed per second. And this stream function is essentially collapsing a complex 3D circulation that I showed you before to a 2D circulation that is poleward at the surface, and it sinks and returns equatorward at depth. But the ocean is density stratified. So before I show you the density structure of the ocean, I wanted to familiarize you with some terms that I use. For density, oceanographers are weird, and we like to use sigma instead of rho, and it's just density minus 1,000 kilograms per meter cubed. And for the isopycnals, those are lines of constant density, which I will show you now. So here I show a cross-section of potential density. It's taken along this transect here. So it goes along the Atlantic Ocean, and it spans from the Southern Ocean to the North Atlantic. And this transect was one that I was on when I did field work. So there's me, the rosette is behind me, it has a CTD on it. I would watch this CTD go down to the ocean floor and make sure that it didn't hit the ocean floor. It did once, that wasn't my fault, but it did hit the ocean floor. It came up with a bunch of like mud and weird stuff on the bottom. But my job was just to make sure it didn't hit the ocean floor, and then I would collect water samples on the way up. And a couple of things, information that it collected was like sea surface temperature, salinity, and here we've got the density. And so these isopycnals that I mentioned before are these lines right here, which are lines of constant density. And basically, there's a couple of features that I would like to point out here. So we've got the flat isopycnals in the interior, and you can see they outcrop at the surface. They're sloped and outcrop at the surface in the North Atlantic. And so when we think about ocean circulation, the easiest way to think about it is if you imagine the ocean like a stack of pancakes. And when you pour syrup on the pancakes, it's easiest for the syrup to travel along the surface of the pancake rather than diffuse into it. The ocean is the same way. Because the ocean is density stratified, it's easiest for water to flow along isopycnal surfaces. And because it's easiest for the water to flow along isopycnals, it's more natural to think about AMOC in density coordinates rather than depth. So on the left is the plot that I showed earlier, which is AMOC in density coordinates, or in depth coordinates, and then on the right is AMOC in density coordinates. And so the benefit of defining AMOC in density coordinates is that it allows us to connect this cross isopycnal circulation with circulation in the interior. So the reason we can relate circulation at the surface to circulation at depth is because we have these outcropping isopycnals in the North Atlantic. And basically the density is going to be changed at the surface at these outcropping isopycnals and not in the interior. And here is another example that I showed before, the circulation in the North Atlantic and AMOC. Here are the outcropping isopycnals at the surface, and then the flat isopycnals in the interior. Any changes in density, like I mentioned before, will happen at the surface because that's where the isopycnals outcrop, and that's where they're open to surface heat and freshwater fluxes. And because flow in the interior isn't changing density, you can see it'll flow along this isopycnal. That means the density is being set at the surface. And so we can connect what's going on at the surface to what's going on at depth. So if we assume the ocean is in a steady state, then we can reconstruct AMOC in density coordinates using water mass transformation. So water mass transformation is the amount of seawater transforming from one density class to another. And the way it does this is through buoyancy forcing. Buoyancy forcing are just processes that change the ocean density relative to its mean state. These processes that can change ocean density can be grouped into two main categories. It'll be water mass transformation due to heat and freshwater fluxes, and then water mass transformation due to internal mixing. And we can see the different processes in this diagram here. For example, for heat fluxes, we'll have latent heat flux, sensibly heat flux, or for freshwater fluxes, will be like runoff or precipitation. So water mass transformation due to mixing is relatively small in the North Atlantic, so I kind of just ignore that term. And I say that the AMOC stream function is relatively equal to water mass transformation at the surface. So to calculate water mass transformation, we use a density flux, which is reliant on surface heat and freshwater fluxes that I showed before. And here we have the density flux plotted, with positive values meaning water is transforming from lower to higher densities, or from lighter to heavier densities, and vice versa. And overlying are the isopycnal outcrops. And if we want to know the water mass transformation, say at a specific density class, so in this black area here that I have outlined, then what we would do is we'd sum up the density flux in that density class, and then we'd multiply it by the density class area. And when you do that, you get a cross isopycnal transport. And I would like to highlight that this density class area is dependent on the sea surface density. So any changes in this sea surface density from either sea surface temperature or sea surface salinity is going to be reflected in the density class area. And then I would also, before I forget, would like to highlight the package that I use to calculate water mass transformation. It's XWMT. It's been a huge help. Jan-Erik Tesdil, John Krasting, Graham McGilchrist, thank you for upkeeping this package and making it available and easy to use. So before I show you my analysis, I wanted to show you what water mass transformation actually looks like, because it can be a bit confusing. And this is basically what it looks like when you calculate it, I'm using output from the community Earth system model. Doesn't really matter, it's not really important part. But the orange line, I'm just trying to demonstrate what it looks like. The orange line here is water mass transformation north of 45 degrees north. And the blue line is AMOC at 45 degrees north. So if we take the stream function and you just draw a line at 45 degrees, that's what AMOC looks like. So if nothing else I said made sense to you, the only thing we really care about is that water mass transformation north of 45 degrees looks pretty similar to what AMOC looks like at 45 degrees north. This is cool because that means we can estimate AMOC solely through surface fluxes and sea surface temperature as well as sea surface salinity, which is important because we have better spatial and temporal resolution of those data sets. And so we can do a more thorough bias analysis of AMOC circulation relative to surface biases. So just to summarize so far, because there's just a lot of information thrown at you, AMOC is important for climate. Climate models are important for studying AMOC, but they have surface biases. Direct observations of AMOC are short and sparse. And AMOC can be represented by surface force water mass transformation through changes in buoyancy, which I showed you before. And these changes in buoyancy are reliant on surface processes, so the surface fluxes and sea surface temperature and salinity, which we have longer and more spatial observations of. Therefore, we can produce longer observational benchmarks of water mass transformation as a metric for AMOC and connect surface biases and overturning, connect surface biases to biases and overturning circulation. So that finally brings me to my science goal, which is to create observation-based water mass transformation benchmarks for comparison to OMIP models to assess North Atlantic biases and their relation to overturning circulation. That's a lot. So I mostly just focus on this first part here, where I am creating the observational benchmarks. And when I create the benchmarks, a couple things that I'd like to look at or do is analyze a spread in the observation-based water mass transformation and figure out why there's a spread, because yes, there will be a spread. And I would like to compare the benchmarks that I make to a low and high resolution OMIP model. And again, OMIP is Ocean Model and Comparison Project. So to calculate water mass transformation, the only things that I need are going to be the surface fluxes, again, sea surface temperature and salinity. To calculate the fluxes, I use two different atmospheric forcing data sets, Core V2 and JRE55DO. And to mention, these are also the same forcings that are used to force the OMIP models. And you'll see that later in the talk. I'll mention the models that I use. And for sea surface temperature, I use high SST and OISST, as well as ECCO SST. And then for sea surface salinity, I use EN4 and ISHI, as well as ECCO sea surface salinity. And so the main difference between these gray boxes and the blue boxes is that all the data in the gray boxes is purely observation-based, so from blended satellites, ships, buoys, Argos, etc. And the ECCO data is a state estimate, which is a little bit, it's kind of similar to reanalysis, but it's a little bit different. But basically, it takes observational data and it uses a model to create or output this data. And the other data sets that I use that aren't as really important is the high SST sea ice, and then for runoff, I'll use the Dye Trend Birth and JRE55DO. So a lot of data sets. And that's because I wanted to calculate fluxes. And so to calculate the fluxes, I use to calculate water mass transformation, I use the CESM coupler, which is, again, the community Earth system model, to couple observational data together. So this is essentially like a data model. I remove all the model components and I just replace them with observational data sets. And then I use the bulk formula to calculate the fluxes. So when I calculate the surface fluxes this way, I can change out the data sets, so the atmospheric forcing or the sea surface temperature, which allows me to look at the direct impacts of atmospheric forcing or temperature on surface heat fluxes and thus water mass transformation. And so when I run the data model with JRA forcing to begin with, and I switch out 3 different sea surface temperatures that I mentioned before, we can get these three different surface heat flux fields, so you say JRA, and then the ECCO SST, OASST, and HAT ASST. Then I'll run the model again. I'll switch out the atmospheric forcing and run it with core V2 forcing with the three different sea surface temperatures, and that's what we see in the right row. And those are just surface heat fluxes. The density flux, as a reminder, is dependent on both surface heat fluxes and freshwater fluxes, but the freshwater fluxes only play like a small portion in water mass transformation, so I kind of ignored that in my analysis. So after I calculate the surface fluxes, which again is right there on the left, I also calculate 9 different density fields. So I have 3 different sea surface temperatures and 3 different salinities that I use. 3 by 3 is 9. And those play a big part in the density class area portion of water mass transformation. So like where the isopycnals outcrop at the surface, it'll be dependent on your sea surface density. And so when I pair the fluxes together with the sea surface density, I have to make sure that I use the same sea surface temperature. So any surface heat flux that uses HAT ASST, I will pair it with a density field that also uses HAT ASST. And when I do that, for all 3 flux fields, essentially I create this matrix of data sets, and I get 18 different observation-based water mass transformation benchmarks. And this is cool because this means that since it's like a matrix of data, I can take a dimension, take the mean across a dimension. So like the mean across any data set that uses HAT ASST or any benchmark that uses HAT ASST, and look at the impacts of HAT ASST specifically on water mass transformation, which we will see later on. So I calculate water mass transformation for the subpolar North Atlantic, which is this full region here. It's all of those colored regions. And then I break down water mass transformation into these different regions to look at the regional differences. And I also use a 1982 to 2009 mean climatology. This is due to data constraints, and all the plots that you see will be using that same climatology. And then looking at water mass transformation, finally, in the subpolar North Atlantic, here are the 18 different benchmarks that I calculated. And just to orient you, we have the density classes on this axis, and then water mass transformation on this axis. And these are all the different benchmarks that I created. I know it's really busy. Don't worry, it'll make more sense later on. But I try to differentiate the benchmarks based on like what salinity or sea surface temperature they used or forcing they used. So the dashed lines will be any benchmark that uses, ECCO salinity. The dotted lines are for ISHI salinity, and then the solid lines are going to be for EN4 salinity. And then the greenish lines are JRA forest, the purplish lines are core forest, and like the hue of the line is the sea surface temperature. It's really hard to tell what's going on, but you can kind of see some groupings of lines, like in this region right here, all solid lines. So any benchmark that uses EN4 as water mass transformation that looks like that in the subpolar North Atlantic. And basically the biggest feature that we can see is this huge spread in water mass transformation based on the different observational data set that was used. It's about a 12 sphere drip spread. And this spread is unsurprising, but it highlights that it really matters what observational product you use when you're calculating water mass transformation. So, finally, we're reaching my first objective, which is to analyze the spread in the observation-based water mass transformation. A couple of questions that I would like to answer is how do different atmospheric forcings, sea surface temperatures, and salinities impact this water mass transformation, and how do the different sea surface temperatures and salinities impact the isopycnal outcrop area and location, and how do different sea surface temperatures impact the surface heat fluxes. So first, to analyze the spread, I looked at the regional breakdown of water mass transformation in the subpolar North Atlantic. Here is the same plot that I showed previously in the subpolar North Atlantic, and then these are the different regions that I break it down into. So the subpolar gyre southeast region, the Erminger Sea, Nordic Seas, Labrador Sea, and the southwest subpolar gyre. And I'm not going to spend a lot of time on this plot because, like I said before, it's difficult to figure out what's going on with all of the lines. But the main thing that we can see here is the spread in the Nordic Sea region. There's a huge spread, and I actually was surprised by this. And so the rest of the talk, I try to figure out what's going on in this region and why the spread is so large. And to make this analysis easier, I grouped the benchmarks by the specific observational product used. And I do this by taking a mean of all the benchmarks that share that same like atmospheric forcing, sea surface temperature, or salinity. That's shown here. So first I look at the benchmarks that share the same atmospheric forcing. And the gray shading is the spread of all the observational benchmarks. And we can see here in the blue line that GRA forced water mass transformation benchmarks have weaker water mass transformation at all of the density classes compared to pore forest. And another feature is that I'd like to point out is that they have the same max water mass, or the same density class where the max water mass transformation occurs. And if I look at differences in water mass transformation due to sea surface temperature, right off the bat we can see that we have this big spread in the Nordic Sea region. And this is due to ECCO sea surface temperature, which you can see in the yellow orangish line. And all the benchmarks that use ECCO sea surface temperature have weaker water mass transformation at all density classes. And high SST and OSST have relatively the same water mass transformation, very similar. Another feature that I'd like to point out is, again, all three benchmarks, or mean benchmarks, have the sigma class, the same sigma class, or density class, where the max water mass transformation occurs. And then lastly, I look at the differences in water mass transformation due to sea surface salinity. And you can see there are differences in strength and the spread of where the water mass transformation is. And basically you can see for ECCO sea surface salinity, it's shifted towards lighter density classes. And in the green line EN4, it's shifted towards more denser density classes. So you see this spread, she kind of like breaks the middle between the two. But you can see this spread in water mass transformation in these density classes here, which is important because that's where your deep water formation occurs. So focusing on why there are differences in water mass transformation in the Nordic Seas due to sea surface temperature. Here I show that the sea surface temperature is cooler than both hot ASST and OASST. The color bar is kind of confusing, so I added some descriptions on it, but the red coloring does mean that ECCO is cooler than hot ASST and OASST. And the bottom plot shows the difference in hot ASST and OASST density. So all the density fields that use hot ASST to calculate it, and then I subtract it from all the density fields that use ECCO sea surface temperature. And then I do the same thing for OASST minus ECCO. And we can see that because we have the cool sea surface temperature bias or difference in the North Atlantic due to ECCO, it causes there to be heavier density in that region as well. Now if we compare ECCO sea surface temperature and the surface heat fluxes from ECCO sea surface temperature, so this plot on the right, you can see the different surface heat flux fields based on what temperature you use, and then the lines are the isopycnal outcrops, and again, those are dependent on the sea surface temperature used. So any density field that uses ECCO sea surface temperature is going to be those isopycnals there, and then same for OASST and high ASST. And So if we compare the ECCO sea surface temperature surface heat fluxes, and we can see that the cooler ECCO temperatures cause there to be weaker surface heat fluxes in ECCO. So these cooler temperatures, weaker surface heat fluxes compared to the other surface heat flux fields. Now if you look at the isopycnal outcrops, again those lines, from the density fields that use ECCO SST, we can see that heavier ECCO density causes there to be more isopycnal outcrops at heavier density classes in the Nordic Sea region. So you can see there's more kind of concentrated lines in the Nordic Sea region. And that is compared to the other surface heat flux fields, where you can see HAT SST and OSST are pretty similar with both the surface heat flux fields and the density or isopycnal outcrops. So to quantify this more, I look at the density class area per density class. So that's just the area of where the isopycnal outcrops at the surface for the different sea surface temperature mean density fields. And it shows that there's a shift in density class area towards heavier density classes for ECCO, which makes sense, is what we saw we actually didn't see that in the water mass transformation, and I'll tell you why. But if I take the average surface heat flux per density class, so if we take these density classes here, in all of the three different sea surface temperature densities, and we sum up or take the average of the surface heat fluxes for those density classes, that's what we get in this plot down here. And we can see that there is a lot weaker and even positive surface heat flux for these denser density classes in the Nordic Sea region. For ECCO, this feature basically cancels out what's going on with the sea surface temperature and the density field. So even though there is density classes right here, we don't see water mass transformation in those density classes because the surface heat fluxes are weak and almost positive, so you're not going to get water mass transformation. And we can see that if we look at, again, the water mass transformation in the Nordic Sea region from the three different sea surface temperatures. We don't see, even though ECCO has a denser density classes, it's more dense than HAT SST and OSST. We don't see that shift in the density classes because it's canceled out by the positive and weak surface heat fluxes. And so the main reason why ECCO is so weak right here is because of the surface heat fluxes. So now moving on to looking at the sea surface temperature salinities and how they impact water mass transformation. Here I show that ECCO sea surface salinity is fresher than both EN4 and ISHI. If we look at the differences in density between the mean of all the density fields that use EN4 and ISHI, so this bottom plot here, versus the mean of all the density fields that use ECCO sea surface salinity, we can see that fresher ECCO sea surface salinity makes the density lighter in the Nordic Sea region. And unlike ECCO temperature, the ECCO salinity doesn't impact the surface heat flux fields. So these surface heat flux fields that I'm showing here are just a mean of all the surface heat flux fields that I calculated previously. And again, the lines are the isopycnal outcrops. And because ECCO salinity causes there to be relatively lighter surface waters, the area covered by these densest isopycnals is smaller compared to EN4 and ISHI, and as a result, that shifts the average surface heat fluxes per density class in ECCO compared to ISHI and EN4, which we will see in this figure. So if we look at, again, the density class area per density class, for ECCO sea surface salinity, we can see a shift in the density class area towards lighter density classes. This makes sense because if there are less isopycnals at denser densities, it allows for the lighter densities to have more of an outcrop area. So you kind of just see that visually, where we've got a lot of isopycnals here, a little bit less in ISHI, and then definitely not as many outcropping isopycnals in ECCO sea surface salinity. And we can see this, so if we look at the average surface heat fluxes per density class, you can see differences in the average surface heat fluxes. This isn't going to be due to the salinity impacting the surface heat flux fields. The salinity doesn't impact the surface heat fluxes. It'll impact maybe the freshwater fluxes, but I don't look at that. But basically the only reason why we're seeing differences in the average surface heat flux field is due to the location and the area of the isopycnal outcrops relative to where the surface heat fluxes are. So now looking at the difference in water mass transformation due to sea surface salinity, again, we can see the difference in the density field in the densest density classes, or the difference in water mass transformation at the densest density classes from the Nordic Sea region shows up in the subpolar North Atlantic. So the main reason why there's a spread there is due to what's going on with weird salinity stuff in ECCO in the Nordic Sea region. So now that we know that ECCO sea surface temperature is cooler and the salinity is fresher than the other observational products, which impacts water mass transformation, I tried to figure out maybe why ECCO has these differences. And the top plot shows the sea surface salinity difference from high SST, so high SST minus ECCO SST, and then the bottom shows the sea surface temperature, and then the bottom is the sea surface salinity difference, EN4 minus ECCO. And you can see co-located with those differences is this difference in, so high SST sea ice concentration, which is the black line, and then the green line, which is the ECCO sea ice concentration. And so we're thinking maybe these issues are embedded, these issues with the sea ice are embedded in the sea surface temperature and salinity that we have from ECCO, and that is causing weird things with the water mass transformation. And these differences in ECCO aren't really highlighted in any paper that I read. That's why I was surprised by this, because when people use ECCO, they use it as like a full product. So when they're calculating water mass transformation, they'll use ECCO fluxes, the sea surface temperature, and the salinity. But we saw that the sea surface temperature is cooler, causes heavier densities. The sea surface salinity is fresher, which causes lighter densities. When you're calculating water mass transformation, those differences kind of almost cancel each other out. Not all the way, as you can see, it still caused problems with the water mass transformation benchmarks. But that's why this hasn't, you would get pretty reasonable values for water mass transformation. So that's why you haven't really seen, I haven't seen this in any papers that I've read. And so I am not totally sure why ECCO is weird, but I want to say the sea ice is definitely a huge cause. So maybe using ECCO is not the best way to go. But a lot of people use ECCO because it conserves buoyancy, which is a good thing when you're calculating water mass transformation. And so it's kind of important to highlight those differences, because when people are using ECCO as an observational benchmark, it might not be a good benchmark to use. And so for the second objective, I just kind of wanted to show how I implement this after calculating and looking at the spread. I wanted to compare the benchmarks to a low and high resolution OMIP model. So I used forced ocean and sea ice models, FOSSI models, and the model that I use, it comes from the Community Earth System Model version 2. And I used two different simulations from this model, which is OMIP 1 and OMIP 2 that I previously mentioned. Again, OMIP 1 uses Core V2 forcing, OMIP 2 uses JR55, and I use the 1992 to 2009 climatology when I'm doing this comparison. Oh, also for the OMIP 2 simulation, I have the low res 1 degree and the high res, which is a 10th degree model. And again, to orient you with this plot, we've got the density classes on this y-axis, water mass transformation on the y-axis, or on the x-axis, and the gray shading is the observational spread. You can see again, the observational spread is very big in the Nordic Sea region, and there's just a couple of features that I'd like to point out. You can see the dashed line is the high-res model, and the red is OMIP 1 and blue is OMIP 2. So again, they're just using two different atmospheric forcings. And the low-res models, you can see in the subpolar North Atlantic, have water mass transformation that's shifted towards heavier density classes. We can kind of see that in both the subpolar dry southeast region as well as the Erminger Sea region. And the high-res model does relatively well, I would say. It matches the observational spread pretty well, and it does a better job of representing water mass transformation in the subpolar North Atlantic. But again, another feature too is in the Labrador Sea region, you've got a lot of water mass transformation in the low-res models and not as much in the observational benchmarks or the high-res model. The key takeaway from this talk, so again, we talked about I calculated the observation-based benchmarks, and then I wanted to analyze the spread based on the different sea surface temperatures, salinities, and atmospheric forcings that I use. There's a huge spread in the subpolar North Atlantic. That's due to the Nordic Sea region. The largest difference in the Nordic Sea region are due to differences in echo sea surface temperature and salinity. And echo sea surface temperature is cooler. That causes their shift towards denser density classes, but the shift is offset by the weaker surface heat fluxes. And then the echo sea surface salinity is fresher, and that causes there to be a shift towards lighter density classes. And the differences in water mass transformation in the densest density classes in the subpolar North Atlantic is going to be attributed to differences in the salinity in the Nordic Sea region from echo. And the second objective, which I just briefly went through, which is to compare the observation-based water mass transformation benchmarks to a low and high resolution OMIP model. And we saw that the high-res model does a lot better job at representing water mass transformation in the subpolar North Atlantic. And then again, I would like to highlight that this work is part of an MDTF pod. This is the NOAA Model Diagnostics Task Force that Liz and I are both on, and we create like process-oriented diagnostic tools. So mine is water mass transformation, and Liz's is going to be AMOC and sigma coordinates. And this is going to be used, or the code can be used to work with a bunch of different models. So you can look at model biases, and my observational benchmarks that I made are going to be part of that as a comparison to do bias analysis. And that is it.
We have quite a bit of time for questions, and we'll start with student questions. Hamish.
Thanks, Taydra. It's a lot of work there, really impressive. The takeaway that I got from that is how uncertain our ocean observations are. And I wonder, like, what's your takeaway there? Do we need to be really careful about which ones we pick? Should we not use ECCO? And like, what's your takeaway from that?
Yeah, so I knew someone was going to ask me, what's the best observational product to use? And that is definitely a really hard question. The reason why I plotted like 2 different observational products versus just the state estimate, which is ECCO, is because I wanted to see if the other 2 observational products that I used were similar compared to ECCO. And I guess if you saw, like HAT-ASST and OASST were pretty similar in the water mass transformation. There was a little bit of difference in EN4 and ISHI when you're looking at salinity, but ECCO is still like a lot more fresh. And so I think when you're trying to have observational benchmarks for water mass transformation to compare against models, I think it's just good to use a lot of different like observational data sets so you do get that spread. But I don't know if I would trust ECCO completely, but like I said, you get relatively okay values for water mass transformation if you use the 2 ECCO products together, so sea surface salinity and temperature. That's because their biases cancel each other out. But yeah, I don't know. I think HAT-ASST is one of my favorites. If I had to pick a favorite, or EN4, those are the ones that I go to. But ECCO is really cool, like I said, if you're wanting to look at the different parts of water mass transformation. So if we saw before, the AMOC stream function is equal to water mass transformation due to surface heat fluxes and freshwater fluxes plus water mass transformation due to mixing. And if we use ECCO, which is buoyancy conserved, we can break down AMOC into water mass transformation and mixing and see like what one causes AMOC to look a certain way. Yeah.
Any other questions? We'll go Nicola and then Clark. Nicola first.
So in your introduction, you mentioned that in the water mass transformation theory, you removed the terms which is about mixing.
Mm-hmm.
So I'm wondering if you have ideas of how you can integrate that, and also if you have like way to quantify, if you don't, how much impact
Yeah, so let me show, let me just click through until the beginning. When I showed, I think it was the CESM2 plot with the comparison. Oh my gosh. Okay, sorry, just flashing at you. Yeah, so I forgot to mention here, the water mass transformation, it's similar to AMOC, the AMOC stream function, but you do see these differences. Those differences are due to what we want to say it's mixing, and I'm assuming it's mixing. It could also be due to volume changes in a specific isopycnal, like outcrop or isopycnal density class. Because we're a volume conserving model, or we're in a steady state, we're not going to see differences in like the volume in an isopycnal class. That term is relatively small, but you can see that we can't fully ignore mixing, especially like in the densest density classes in the Nordic Sea region, and then maybe closer to like the subtropical gyre, which are going to be these density classes. But yeah, relatively, it looks pretty good. Though we don't get the mixing values from the model, so it's like really hard to calculate that term. And mixing is just going to be like a residual term. Like I said here, the water mass we have the AMOC stream function, which is equal to the water mass transformation due to surface buoyancy forcing, and then water mass transformation due to mixing. And yeah, that term is small, so we can ignore it. But we do have small scale mixing like eddies and whatnot. But the main way that density is going to be changing is through these buoyancy fluxes. But yeah, it's just a residual term. So to calculate mixing, which people that use ECCO, when they calculate mixing, they just subtract the water mass transformation to the surface forcing from the AMOC stream function, and they say that's mixing. So when you have problems with your surface forced water mass transformation, then you're gonna have weird values for your mixing then. So yeah, I guess it's important. So we don't really have a way to quantify that. But there is some work being done actually to do that, but I don't focus on mixing.
Claire.
I had a very similar question, so I'm gonna come up with a new question. So this is kind of similar to something we were talking about the other day, but with the high-res model, like my intuition would tell me that the high-res would help with like those mixing things, right?
Mm-hmm.
So I can't really intuitively understand why it would do so much better with the surface heat fluxes. Do you have any intuition about that? Or
Yeah,
any
I'm
ideas
trying
why
to-
the high-res is so much better with the surface fluxes?
I'm trying to show the plot, I can't find it. But yeah, so the high-res is a lot better, and I honestly think it is just due to the resolution. You're able to resolve some of the mixing features, but at the surface, we're looking at like time mean water mass transformation, like a climatology, I think it was like 13 or 14 years. And so like the mixing at the surface and all of that stuff isn't gonna really be, I think, that important when you're looking at water mass transformation, because we're looking at we're taking a mean, we're averaging it out, if that makes any sense. But I think just resolving specific features like bathymetry in the high-res model is important, because like I mentioned before, you have the North Atlantic current path, and if there's a bias in that path, which we see in the low-res models, like if the North Atlantic current is shifted, more south, then you're gonna get like a fresh and cold bias in that region, like I showed. And that bias is a little bit better in the high-res model, and so I think that's why your water mass transformation looks better, or it matches the observations better, is because of the North Atlantic current pathway. And that's actually the work that I want to look into for my next chapter, and I'm trying to figure out, like, is the bias in this North Atlantic current causing biases in overturning circulation?
I have a follow-up question with what Nicola and Clark was going to ask as well. is that other than the mixing term in the future figures, we also get rid of the salinity term. And do you think that as from future climate perspective, once we have like more ice sheet melting happening across Greenland, do you think that that melting of ice sheet and then the freshwater flux because of that would make that term important, or it would still be? Like, what are your intuitions?
So if you're just like dumping a bunch of water into the ocean, like you see in those hosing experiments, yeah, definitely would be important. But I think I wish I had a plot or an example of what water mass transformation due to like freshwater fluxes looks like compared to heat, and or heat fluxes. It's very, very, very small. But I do think, obviously increasing melt from these ice sheets and everything is going to impact the freshwater fluxes, but I don't know exactly how much it would. I think just a small amount. But yeah, it does play a part though. That's why I actually like the sea ice issues. You can see the differences in water mass transformation, I think, due to like the sea ice issues. But that could also be due to the fact that like you have the sea ice, you can't have surface heat fluxing as well. If that makes sense, it insulates the ocean, so it has both salinity and heat flux type issues. Yeah.
Thanks. Do we have questions on Ryan?
Couple things. Liz said, in response to Clark, she said all of what Taydra said, plus increased resolution also affects air-sea coupling, in other words, heat fluxes, potentially improving it. And then Nuo had a question. She said, is sea ice output stored from the CESM runs? Have you compared the sea ice concentration difference between ECCO and Hattie SST or OISST?
I compare, so you're saying like comparing like the sea ice from the models to the observational sea ice? No, I have not done that yet, actually. But that is what I'm doing in my second paper, or my second chapter, is I'm looking at like how sea ice concentration looks like in a bunch of different models compared to the observational benchmarks, and how like the water mass transformation looks compared to sea ice concentration and mixed layer depth and like other certain ocean metrics.
We can move to Till and then John. Till first.
Wonderful talk. Thank you. Really enjoyed it. So ECCO has known biases in the Arctic, right? There are Arctic-specific state estimates. There's like this ASTER product.
I haven't heard of ASTER actually.
Yeah, there's a couple of reanalyses that are explicitly focused for. So it might be worth looking at one of those.
Yeah.
And then I just wanted to mention, I looked at exactly that region at exactly the same time period for the phytoplankton
Yeah,
stuff.
I remember you looking into that.
And I found exactly the same.
Yeah.
So I have that figure in one of the papers.
Nice.
Where you have the different CIs
Yeah.
between the, and like, in response to you, I think the observations of especially the CIs are very accurate. And they correspond very nicely.
Yeah.
And so the ECCO is just wrong.
Which
I mean, in this
sucks,
region,
because it's a cool product to use.
Yeah.
And I know, like, I remember at Ocean Sciences, they had a whole thing on ECCO, and I do remember them mentioning that there are sea ice issues. They need more data for that, because, like I said, ECCO has a model component to it. But, yeah, it does very poorly in the Nordic Sea region.
John?
Yeah, I think it's related to my question, although I asked you, Taydra, I'm really naive about all this stuff. In the Norwegian Sea part of the domain, is that just the fact that the water is considered colder and fresher in one of those data sets? Is that over melting ice? Is that how it gets that way? Because I would imagine a sea that is traversed by cyclones has a dump of water into it, so that's part of the freshening. But then on the backside of the storm, there's enormous evaporation. And I would think that maybe that balances out. So I just don't know how the water gets both colder and fresher.
Yeah, so the water is getting colder because it's traveling, to the poles. And so that definitely has an impact on the density. But also, yeah, I think you're talking about like the cyclone tracks maybe like over here. And that is gonna, I don't know how much, that's actually a good question, looking at how like cyclones or storms impact water mass transformation, and that is something that I discussed with Ruja the other day, because it will impact the surface heat fluxes, but I'm just looking at like long timescale climatology type stuff, so I don't think I would be able to see like differences in water mass transformation because of cyclones based on the climatology that I'm using. But if I were to look at, you know, maybe variability in water mass transformation, it would be cool to see if, you know, cyclones or storms impact that. But it gets fresher because we've got the sea ice melt from Greenland. We've also got some freshwater output from the Mediterranean Sea and some other place. But yeah, it's gonna get colder and fresher due to like where the region is. So obviously in the Nordic Sea region, we have the coldest waters here because it's really far north, but it's also fresh because we have melt. If that makes sense.
Thanks.
On the topic of your surface heat fluxes, some of those differences are on the order of 100 watts per meter squared, which is huge. And I was wondering, have you thought about trying to constrain some of those realistic surface heat fluxes? And I think it's bold to call JRA heat fluxes as observations, and there are a lot of observations of heat fluxes, heat flux from NASA and OA flux from Woods Hole. And I wonder if you've tried to constrain some of these to realistic surface heat fluxes to narrow down your population.
Yeah, I haven't tried that, but JRF-D5DO and CoreV2 are like flux balanced, and so yeah, you're not gonna have like any imbalances with like the energy, and so in using a flux balanced data set when calculating water mass transformation there's a couple of studies, like I think Grootkamp and Ayudakane 2018, I believe, showed that using a flux balanced data set versus one that's not has an impact on water mass transformation, but I haven't tried to like constrain the like JRA55DO and CoreV2. I haven't looked at like the direct observations yet, but that would be interesting though to look at.
It might be quite easy to like say that one of these maps is completely wrong because it's 100 watts per meter squared off for a certain region over there.
Yeah, and I mean, this is crazy to me. You are gaining heat in this region, which doesn't make sense. Yeah, you're very far north.
I guess you have no way of breaking that down if it's a method of cooling or sensible heat fluxes. Or...
I actually could. So when I do calculate the fluxes using the CESM2 coupler and the bulk formula, it outputs like the specific flux. So flux due to like runoff, or I have to like do some calculation and convert. But you've got runoff, like surface heat fluxes, like the long wave radiation, short wave, sensible heat flux. I have all those separated, but when I'm looking at the surface heat fluxes, I just look at the total net, same for the freshwater fluxes. So I could break it down into the individual fluxes, or individual parts of the fluxes, but I haven't done that, but it would be interesting. It's just lots of different ones, lots of stuff going on, yeah.
I think with that last question, we can conclude the talk again. Let's thank Taydra one more time. And our next seminar will be next Wednesday, so please show up next Wednesday again.